Hi, today I'm back on the ALU. What I want to work on today is integrating the adder and the flags. I'm going to stick a list of goals up, and I think I'm going to try this out and see how it works. What I want to accomplish today is I want to extract the flags breadboards from the build, and there's some associated cleanup that needs to happen when I do that. I'm going to need an inverted carry signal, and I don't want to invert it in real time. I want to have that pre-calculated and latched. So I want to add that into the latch. I'll get more details on that when we get to it. I also want to add a line driver for the adder results so that those can be pushed out to the main bus. I want to connect the adder to the flags input. In other words, I want to make sure that the results of the addition can properly populate the flags. And I want to set up all the ALU inputs, including the carry flag coming in. And of course, I'm going to collect all the control signals into one place so that I can jump off the breadboards and integrate that back into the control logic. There's quite a bit here, so let's get right into it. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. Okay, I'm still here with my R1 register tests that I had in the last video. And the only thing I've changed since the last video is this cable, which was tightly run underneath all of this and was really tight here on the corner. And so I've replaced it with something that's a little bit longer, will kind of hang off the front and not quite get in the way. The flags are all located here on these breadboards. The goal today is to extract those off the breadboards, or one of the goals today, and then add in the adder breadboards that I have put together a couple of videos ago. So let me get into that. I'll get this extracted and then we'll come back and be zoomed in on the task at hand. Okay, after turning power off, first thing to do here is to separate the breadboards so I can identify what wires I need to deal with. Then the 4 flags for output are carried over to the inputs that go into the instruction register before the latch. Now, there are 4 lines that are kind of hopped halfway through, so I've replaced that with a 4-line ribbon cable. I'll tuck those under the breadboards just to keep them out of the way. Next, I've got the clear carry and set carry control lines. I'm going to have to check that and make sure I didn't confuse the 2 signals. I did get those switched around and I corrected that off camera. Now I'll just tuck those 2 signals up out of the way so I can continue to extract the flags. Okay, there's one more signal here I wasn't taking into account. This is the clock signal I need for latching the flags. And for now, I'm just going to go ahead and set that aside, and I'll have to come back around to that when I hook this back up. Okay, I am zoomed in here pretty good, and I'm going to stick up in the corner over there a pin diagram of the 74LS74 D-type latch that I've got here. Here are my signals. I'll stick those down here. And from right to left, I've got clear carry, set carry. Then I've got my Z flag data and latch signals. Those are these 2. And these 2 controls are orange, and they are passed off. Now, why am I seeing this incorrectly? They are not orange, they are green. And green is passed off to this first latch I see. The next one over is orange, and they're passed off to this one. So this is my carry for both the user flags and then the interrupt flags up here. Pin 6, which is going to be this position right here, is the inverted flag, and this is for the user side. Pin 8, which is going to be very difficult to see, and my head is probably in the way, but it's this pin right here, right on the end. And finding a place to drop a wire in here is going to be a challenge. But pin 8 is the inverted for the interrupts. And so the key now is my signals exist. I just have to route them to where I need them. The user one is going to go up to this position. Now notice I've got this pulled high at the moment, and I will grab a pair of pliers so that I can pull this out. I don't need that anymore. All right, where the heck did that? Oh, that was on here. And then similarly, if I can find the right spot to put this, this one will go up here to this position, and I've got a pull down here that I need to remove. All right, that brings the signals to my line drivers. Now both of these then need to be brought from this position back here to my line driver for output to the LEDs, but here's the key. I'm not actually going to output that. That's only being brought over so that I have a common spot, so that I have a common location here that I can pick this up and route. So each of these positions here become a single node electrically. And so if I tie in anywhere along here, I can actually pull that common inverted carry flag down to my carry flag inputs. I hope that makes sense. That said, I need to get some wires out, and I need to get this cleaned up so that I can focus in specifically on getting the adder added in down here at the bottom. And once again, I've got them hooked up here. I've got this pulled down here. So we'll pull that out. Okay, with that complete, the point is now that I need to be able to latch, and here's my latch I see up here. I need to be able to latch that inverted carry so that it's available in the next clock cycle. I need to create that delay. Now in my latch I see I've got this particular signal pulled high. I'm not sure why I'm latching a 1, but let's go to CircuitVerse and find out. Okay, we're dealing with the ALU flags. No, those are the actual D-type latches. These are the line drivers that then combine to, there would be a line driver inserted in here. So conditional execution, there's my latch. And yeah, I've got a 1 set to be latched, which passes on to the multiplexer, the 74HC151 multiplexer, which selects which one of these lines should be able to go. I should, in all honesty, be able to do this. Yeah, it's just an input. I should be able to have my constant wired into the 151 directly, and then my inverted carry, which I will add back to the flag's output. Now, where's my inverted carry? This is no longer a 1. That comes straight to there. This is no longer a 0. That comes straight to there. I'll stick that down there. And this now gives me my carry inverted, which comes up to this signal. Now I will need to pull the carry out as well. I will do that later. Let's make these changes on the breadboard. Okay, these changes are relatively simple. This line now is eliminated. This is moved over to this position. And then ultimately, I like that word, this now comes up to here. So now that is the point that I will take my inverted carry off for the ALU input. Okay, the next task here is going to be to revamp the ALU adder such that I have line drivers to drive the LEDs rather than combining those signals. It's one of the design tenets that I've been following. And then I also need to drive the result out onto the main bus. So I'm going to separate these two breadboards, but in order to do that, I want to make sure I keep all of these signals in order. So I am going to pull them back to one breadboard, and I know I'm plugging them into ground here, but that's just so that I can keep everything straight until I can hook them up into their final destination. Okay, same with the carry output. For this breadboard, I'm going to separate this. Sorry, it's just a simple knife, guys. I don't live where we use a short sword for a knife. And then I've got my old register sitting here, and I'm going to scavenge off of this because this can all be pulled apart. Okay, first order of business here is power and ground. Plus, I want to make sure that I take care of the decoupling capacitors. I need the 47 microfarad for the power rails, and then the 0.1 microfarad for each of the ICs. Next up are the line drivers. I've got 2 for the main bus, and then 2 to drive the LEDs. Don't forget power, ground, and decoupling. Now I'm going to scavenge the wires off the register breadboard because they're already cut to the exact length I need. And then I'll just replace the temporary wires back to where they came from so I know where everything gets hooked up. I'll take a second to sort out the control signals now before everything gets covered up. And now the ground connections for the LEDs. I'm going to bind them all together like I had them before, but I'm going to insert 4 connections to ground instead of just 2. Now the signal wires for the LEDs. I have some longer ones and some shorter ones, and I ended up putting the longer ones on the shorter side, so watch me do this twice. And finally, the ribbon cables as placeholders. And now for the long process of replacing each of the temporary hookup wires with a more permanent wire. Because some of these are coming from the bottom row, I have to go up and over a lot of existing wires to make that happen. So it's a lot of 3-dimensional wire bending again. Okay, so my carry input and my carry output. The rest of this is done. Now we get into taking the results of the add operation and turning those into inputs for the flags. And for that, I believe I'm going to need a couple of additional breadboards. So I have zoomed out a little bit to give me the room that I need to be able to show everything. Okay, just fits. And again, I'm going to scavenge off my register board here and collect power and ground. Okay, it adds in the decoupling caps that I need. I got one extra. The decoupling cap that I need. Now let's take a look at CircuitVerse and determine what we actually need to do. Okay, so the hardest flag to calculate is going to be the 0 flag. And that's simply because all of the outputs need to be compared to 0 and a determination needs to be made if all of them are 0. Now the easiest thing, most ideal thing would be a 16 wide NOR gate. That would be the trivial calculation. Such an animal doesn't exist. So to get around that, what I've done is I've inverted every signal and run it through an 8-wide NAND gate, and then from the result I can then NOR the 2 bytes worth of 0 flag together, and that should give me the 0 flag that I'm looking for. On the screen I've got all of my inputs set to 0. I've got all of my outputs are calculated at 0, and my 0 flag up here is on. And if I change any one of these bits, the 0 flag goes off. Let me show you what I found in order to put this together. So for this to work, I need two 74LS30 chips. These are the 8-input NAND gates. And then I need a 74LS02, which is 4 2-input NOR gates. But the real magic here is going to be these two 74HCT540 chips. Now I got HCT simply because there's other instances where I may need to drive some HC logic from LS logic while I'm building it out. So I chose to get the HCT, and I don't believe that the LS versions of these were readily available. They have exactly the same pinning as the 74LS541 ICs, meaning it's basically a line driver. What's the difference between the two? The 74LS or HCT540 IC inverts its output. That means I basically have two 8-wide inverters that are going to invert the outputs that I need so that I can put them up into the 8-input NAND gates and then through a NOR gate in order to properly calculate the Z flag up here. Let me get this all wired up. Once again, I start with power, ground, and decoupling. Since I'm scavenging, I'm having to reform the leads on these capacitors. Next, I extend each bit from the adder result up to the inputs to the inverter. And then I need to take care of the output enables. Next, I extend the outputs from the inverter line driver up into the 8-way NAND gates. Now, the last thing I took care of was extending the outputs here from this pin and this pin over to the 2 inputs of this NOR gate up here, the output of which now becomes my 0 flag data. Now that happens to be this pin here, so this can get relocated down here. I'm going to drop this down one, and then I can take an extra wire here and connect both the user side and the interrupt side. So let me try a different pointing device. I can connect both the user side and the interrupt side of the 0 flag data up into the output of this NOR gate down here. So it's the control signal of the actual latch, which is here, that's going to control which of the 2 flags are actually going to latch for that operation. Okay, let me get this all replaced with some more permanent wires all the way up here to the Z flag, and then we'll move on to the other flags. Okay, that completes the Z flag itself. Okay, I've zoomed in quite a bit here because this next bit's going to be a little difficult to see. Next up is my carry flag. It's the next one along as I'm going right to left of these signals. They're up here off the screen. So what I want to do is I want to replace the carry output with a longer line and bring it up here. Where is inconsequential at the moment, but then sliding this down, I want to extend that also over here to where this blue line is, which is really my carry flag input into the flags. Now I also need to extend that up to the interrupt flags as well. Just like I did with the 0 flag, I want to make sure that the same flag is available to both. Both flags latch registered. The next one up the food chain is the N flag, which is a negative number. Now a negative number is quite simply the most significant bit, which will be this bit right here. And my N flag, that's my latch, it's this white one here. My in flag will be plugged in right here. And again, it will be carried up to the interrupts as well. Finally, we've got the overflow flag. And for that, I need an exclusive OR gate. That looks like as good a place as any to put that. I'll get power and ground in a second when I do the cleanup, but the overflow flag is an exclusive OR of the carry flag coming out of the most significant bit. And again, that's exclusively ORed with the carry flag coming into the most significant bit. Well, that carry flag is down here, and this is what was difficult to see. This is this green line here, which comes off of the previous adder here. Move that out of the way so you can see it. Comes off the previous adder down here and is brought over as an input into the 5th adder here. So this is my carry input into the most significant bit. And its output then becomes my overflow bit. Okay, let me do that cleanup, and that'll take care of all of our flags output. I'm making an attempt to keep the colors the same as the flag inputs as I've got them laid out on the flags latches. I ideally would have pulled out each of those data lines and rerun them to their source, but I honestly didn't think about that until right before I started this voiceover, so there you go. Making it up as I go along. Okay, that leaves me my control lines for the user flags. I need to duplicate these for the interrupt flags up here. Then I've got clear and the selection between interrupt and user flags that both need to be addressed here. Okay, the next task I want to take care of is the inputs to the ALU. One of those is the carry flag input. It's a relatively simple circuit here, or at least that was my original plan. It's flawed. Stick with me here and I'll explain what's going on. What I wanted is I wanted to be able to make a selection between one of 4 different values that would be possible on the carry input. I have a need to be able to force the carry input to be 0. I have a need to be able to force the carry input to be 1. I have a need to be able to take the carry flag from the previous operation and feed that back in. And then I believe I'm going to need an inverted copy of that previous flag. And I started off earlier in this video creating the circuit for that. Now, of course, I need to have those 4 values available to me based on the program context and the interrupt context. So I needed to bring the interrupt context or X flag into this selection as well. But again, it's flawed. Let me go to the breadboard and I'll show you what the concern is here. Okay, so quick reorientation here on the board. I've got all of my flags captured here by these D-type latch chips. The bottom is the program or the user flags. I use those 2 terms interchangeably. I really do need to settle on using just program flags. And then the upper ones up here are the interrupt context flags. Both of those are brought up into these line drivers here, whereby I can make a selection which set of flags are actually active based on this X context flag that is maintained in the control logic. These signals are brought here to this additional line driver. So the outputs of the line driver are brought and combined into the inputs of this other line driver, which drives the LEDs. So it's inconsequential in the overall scheme of things, except in that all of these nodes are brought together and are effectively the same. Now here is my flags latch up here. And because I am selecting back and forth between which line driver is actually going to be presenting flags to be latched up here, I've already taken that X flag into account. And so there's now no need to bring that X flag as part of the selection because it ends up being redundant here. And I'm going to take the flags directly off of the latch. Why do I prefer the latch over the direct inputs here off of these latches? For timing purposes. My belief is, and I may find that I'm wrong, but my belief is that I need a half clock cycle delay between when this will latch and when this latches, so that the next operation can come in here and update these flags. So I need to build that extra half cycle delay in, and that's what this latch is intended to be for. So with another 74 LS151 down here, this is going to end up driving my flag input, but I only now have 4 selections I need to worry about. The selection for the most significant bit on here is now inconsequential because, again, it's handled up here by this particular latch chip. So while I get power and ground, let me get a copy of the pinning up on the screen. So if not you, I know what I'm doing. And we will get this wired up. Okay, so
my C input, which was my
context flag, I'm going to drive low. I'm going to pull it directly low. Not going to need that. Both B and A here are going to come off the control logic. Next to those are the 4 high order inputs, and I'm going to tie all 4 of those low. They are not going to be used anymore. On the bottom down here, I have inputs for carry, which is going to be bit 1 or data element 1, which is pin 3. Next over is my new inverted carry, and that's going to be data element 2 or pin 2. Then I've got a force 0, which is pin 4 or data 0, and I've got a force 1, which is data 3 or pin 1. G is an output enable, and that I'm going to tie directly low, so that is 7. And then my output now, which is, well, shoot, I gotta go look that up. I believe it's Y. Y is the output that I need. Pin 5 is Y, so this is my carry input all the way down here off the bottom of the screen. Here's my carry input, and that's going to move up here to pin 5. Wrong 5. Pin 5. Pin 6 is going to be unused. Let me get this cleaned up. Okay, I tried this once and I made a mess of it, so I'm gonna re-record this. The next step here is to deal with ALU A and ALU B, and I've got the 2 breadboards set. Power and ground's already set for the 2 of them. Here's my ALU A inputs. Up here are the ALU B inputs. And each of these, for the ALU itself, the ALUA is going to have several different places that it's going to distribute that signal to. So I need a demultiplexer, and I'm going to bring up for myself a pin diagram, and I'll have one available for you as well. A, B, and C are pins 1, 2, and 3. Next to that is 3 enable pins. So 1 active low, 1 active low, and 1 active high. Now, power and ground have already been taken care of. Here's my decoupling. Here are the line drivers that are going to become the signals for ALUA. All right, so output 1 is going to end up being the enable for these 2 line drivers up into ALUA. So let me get power and ground here as well. Again, decoupling. And then the other enable pin, pin 1, is going to be tied low so that the demultiplexer is actually driving the outputs. Okay, I want to duplicate this circuit down here for ALUB. Okay, that looks properly duplicated. Okay, next up then is going to be to tie my 16 outputs of ALUA up here to these points. Okay, and then B are going to all be up here. And then this then gives me the ability to drop in my ALUA input and then my ALUB input. And then these will go off to the different buses. The last task here today is going to be to take these control signals and extract them out onto the breadboard here in such a manner I can plug control wires in the form of a ribbon cable in and control both the program side and the interrupt side of the flags from the control logic. And so these are going to be hard wires as well. And then I've got this signal, which is the X flag indicating which context I'm in. So I'm going to pull that down as well. This ended up being a little bit fussier than I was anticipating. I'm making an effort to keep the colors of the hard wires the same all the way through so I can trace each flag by color. Makes it a little bit easier for debugging. Ultimately, I ended up leaving the X context flag as a temporary hookup wire, and that's for the number of signals that I need to bring across. I'll end up converting that to a hard wire later. Finally, down here, I've got two signals to indicate ALUA input and two signals to indicate ALUB input. And currently, I only have one input, and I don't expect it to go beyond 4, at least not yet. So I'm going to tie the most significant bit here low, meaning I will be using 0 and 1 and 2 and 3. And if I have to expand beyond that, then I will remove the pulled low signal. That said, there's 5 signals here, double that, that's 10, so that's a total of 11, 12, 13, 14, 15, 16, 17 signals I need to pull from the control board. Well, there's 18 if you include the ALU output enable. 18 signals that I'm going to need to pull from the control logic. Now I can pull the 5 interrupt related flag signals off, and I can leave the X flag tied low for now, and that's going to save me 6 of those. So that brings me down to 12 signals, and that's still far beyond what I have available to me, which means I absolutely have to get this EEPROM replacement circuit working right, or I can actually keep power isolated to this and not try to actually power the entire build from this battery. Okay, so the next video was slated to be the R2 register, including that into the build. I do have some problems that I've got to solve, not the least of which is this, and I still have some power issues that I've got to get through where my power supervisor is complaining. And so I'm probably going to have to insert a dedicated video in there either before the R2 register or after the R2 register to address my custom EEPROM replacement and power issues and the other things that I've got to take care of. So I have parts for this that are scheduled to be delivered tomorrow as I record this. And so depending on how that goes, the next video may be the troubleshooting and hopefully issue resolution, or it'll be the R2 register solder up and then adding that into the existing instruction set, including being able to move information from R1 into R2, which would be really nice to be able to do as well. We'll see you soon.